Hello everyone. Today we are going to be talking about distributed forces, specifically of centroid of lines and wires. Here is the general formula for the centroid of a line L. We can find the x and y coordinates. The x coordinate is called x bar, while the y coordinate is called y bar. So the x bar we can find by integrating x times the differential change in length over the total length of the wire. The y-bar is found in a similar method. It is possible in many cases to determine the center of gravity of a composite wire or the centroid of a composite line by dividing the wire or line into simpler elements. As seen in this series of pictures, divide line into elements. Element change in L at a point xy, the order pair xy, and then the centroid is located at x bar, y bar. Again, we can express x bar and y bar in this method, relating it to integration. So centroids here is kind of a small animation for you guys. Basically, we're trying to balance this wire on your hands. But if the mass of this wire is uniformly distributed, the centroid corresponds to its center of gravity. Centroids of common shapes of lines. Here are some shapes in their x bar and y bar components. Quarter circular area, and semicircular arc, and the arc of a circle. We can see the x bar and y bar expressions on the right. Statics problem for centroid of a wire. Here is the problem statement. The homogeneous wire ABC is bent into a semicircular arc and a straight section as shown and is attached to a hinge at A. Determine the value of theta for which the wire is in equilibrium for the indicated position. So we're going to highlight some keywords. The wire is homogeneous, which means that the mass is distributed evenly across its entire length, which means constant density at every specific point, which means that the center of gravity corresponds to the centroid. It's bent into a semicircular arc and a straight section. We can thus divide it into two portions, and is attached to a hinge at A. We want to determine the value of theta for which the wire is in equilibrium for the indicated position. And equilibrium here is a key word because that means that the sum of the moments about A must be equal to 0. Here's the problem statement again, the problem diagram. We are given that the semicircular arc plus the straight section forms the total wire, the hinge at A, and we want to find the value of theta for which the wire is in equilibrium. So our solution now, we will first divide the bent wire into a straight section and a semicircular arc. As such, a straight section in purple and a semicircular arc in green. We want to find the x bar and y bar of each section. Note, for equilibrium, the center of gravity of the wire has to lie on a vertical line through A. Since the wire is homogeneous, the center of gravity is equal to the centroid. Thus, x bar of the whole figure, the whole bent wire, is equal to 0 for the whole bent wire. And we actually do not need to find the y bar of each section. Oh wait, no, that's not the reason why we don't need to find the y bar. But basically this is helpful because we know that the moments about A must add up to 0 if we take A to be the origin. We do not. So here is another animation. You can see that the whole figure is in equilibrium. So this means that the centroid corresponds to the center of gravity. Okay, next we want to find the x bar and y bar of each section. For the straight section, we can draw a triangle, a right triangle, and then the centroid, this is the approximate location of the centroid. We draw another triangle over here. Those two are similar triangles. And then we have theta over here. The length of the adjacent side is r cosine theta by Pythagoras theorem, since we know that the length of the whole length of the purple section is r, and then we have theta, so r cosine theta is the length of the adjacent side. And then since using similar triangles, we can know that the right half is equal to r cosine theta over 2. Thus we have x, the x centroid, x coordinate of the centroid for the purple part of the wire is r cosine theta over 2, except it's negative since it lies to the left of A, which we're taking to be our origin. The semicircular section, we will recall that a semicircular section, the x centroid, the x coordinate of the centroid is 0, while the y coordinate is 2r over pi. But we have to reorient our semicircle to match our figure. So this means that instead of x bar equals 0, it will be y bar equals to 0, while x bar will be equal to 2r over pi. Keeping that in mind, we can locate the approximate location of the centroid for the semicircular arc, which lies some distance to the right from the origin of the circle, from the center of the circle. That distance will be equal to 2r over pi from the table we just saw, or from the table to the right. We draw a triangle. We remember that this section is r cosine theta. So this small section over here, which is the distance of the centroid of the semicircular arc from A, the origin will be equal to 2r over pi minus r cosine theta. So there we have it. And then now a brief recap: the solution, first step, second step, and then the straight section, which we found to be x bar equals to r cosine theta over 2. But remember that since the centroid here lies to the left of A, it will be negative. So we have to change this a little bit. The semicircular section, x bar is equals to 2r over pi minus r cosine theta. The sum of the moments about A will be equal to the x bar of the whole centroid times the length of the purple section, which is r, plus the length of the green semicircular arc, which is pi r, which is equal to 0. The sum of the moments about A has to be equal to 0. And this is in turn equal to the coordinate, the x coordinate of each centroid multiplied by the length of the wire at each point. And then we thus have cosine theta is equal to 4 over 1 plus 2 pi equals 0.549. So theta, taking the arc cos of each side, we will have 56.7 degrees. So that is our final answer. Thank you guys for watching this video. I hope this video helped you in your statics endeavors, and I hope you guys learned something about centroid of lines. Keep with me for the next video.